let's continue on. I think we'll finish with chapter 1 today, and then we'll move on to chapter 2. We probably won't get entirely through chapter 2 before the exam next week, so we'll get as far as we get. And yes?
So will the exam just cover everything that we've talked about until the day of the exam?
Yeah, the exam will cover everything we've talked about until the day of the exam, yeah, basically.
Are we taking it in the testing center?
Are you taking it in the testing center? That's currently my plan. That should give you the flexibility to do it whenever you want. I know it's kind of a pain. Last year I did the exam in oral exam format, so I actually gave out the exams ahead of time, and then people prepared, and then they came to my office and I asked them a question of my choosing, and they got to answer another question of their choosing too. And it went okay. It took kind of a lot of time. So I don't know. We may try that a little bit later. It's kind of an interesting format.
Let's give it a try.
Let's give it a try.
Yeah.
Probably not for this time.
So the format of the test, how is that going to be?
The format of the test will look very much like the practice exam that I gave you.
Oh, we have a practice exam on Learning Suite?
I thought maybe.
We very well could. I might have missed it.
There should be one on Learning Suite. If there's not, I'll check it after class.
Okay, perfect.
Yep. That was actually last year's oral exam, so you get an idea of what. I would do it exactly the same way, only you would just write your answers. Okay, so we're going to finish up today talking about how to use group orbitals to deal with some interesting challenges with structures of molecules in organic chemistry. I think the first thing I want to point out, which I don't think we need to spend too much time on, is that because of the symmetry of these orbitals, particularly for the bent CH2, notice that we have one or of those group orbitals, the 2py, that's orthogonal to all of the others, so that we can consider the orbitals that are made by the 2py independent of any of the others. And you'll notice that we did that last time when we talked about ethylene. Notice that we got these two, HOMO and LUMO, from only the 2py. And similarly with formaldehyde, you'll notice that the 2py orbital only ends up being involved in the pi bond and in the LUMO. So that's one of the neat ideas in organic chemistry, that you can often deal with pi bonds independent of the sigma bonds. Sometimes people call that the sigma framework. So as an example, if you think about the allyl, what's my problem here? I don't know. I'm trying to figure that out for a long time. Here is, let's say, the allyl cation. If we want to understand what's going on with the pi system, we can ignore the sigma bonds. We don't have to sort of worry about that group orbital picture, and we can just think about how to combine the three 2py orbitals that are coming out at you on the allyl carbocation. Now, we've before only mixed two group orbitals together to get two new molecular orbitals out, but there's no reason we can't mix three or any arbitrary number of group orbitals together to get molecular orbitals. And how you do that depends, how you mix these three together depends on the shape of the molecule and the symmetry that you've got. It's easiest conceptually to figure out how to mix these three py orbitals, and I'll just remind you of our coordinate system. This is x, this is z, and this is y, so coming out at you. The easiest way to do this is to first think about, okay, let's add, let's mix the 2py from carbon 1 with the 2py from carbon 3. Why would we do that? Well, just because it's easier. So this would be the, we're looking down on the molecule. So here is the upper lobe, and in the back, the lower lobe of the 2py orbitals on each of those carbons 1 and 3. This is the plus combination. So I don't know whether this is 2py1 plus 2py3. And then we can draw the minus combination. And the thing that we notice, or should notice here, is that because these orbitals, as we've mixed them, are far away from each other, we don't really expect stabilization. Right? As we've drawn it, we haven't added in anything on carbon 2. These are far enough apart that the 2py1 minus 2py3 is the same as the plus combination. Right? So that's where we are. We've got both of these varieties. Then we're going to mix in, and by mix we mean mathematically the plus and the minus combination. We're going to mix in the 2py orbital from carbon 2, and we'll do the same here, mix in plus or minus the orbital, if we can, 2py2. So if we do that here, we're going to get two different options. So this one that I'm going to draw will be the plus combination, where we add in 2py2. So I don't know how we want to name these. This is just sort of helping you hopefully keep track of where everything came from. This is the plus combination. And then you've got the minus combination. And maybe I should put the plus combination sort of lower. And then we'll put the minus combination here. And now they're no longer equal in energy. And the reason they're no longer equal in energy is because this orbital has no nodes all across the molecule, whereas this one has two. And I'll just point out, when we draw the molecular orbital this way, what we mean to communicate is not that there are three different p orbitals on those atoms, but that this orbital extends over the whole molecule. There's a lobe of one wave function sign on the top, and then in the back below the page there's another lobe of the opposite wave function sign. It's easier to draw it like this, and this way you can see where we've gotten this orbital from, that we've added all of the p orbitals together in phase. Well, what about this one? On carbon 2, it just so happens that carbon 2 coincides with a place where wave function equals 0. Right? That's a node. So it doesn't matter whether we add in or subtract out the 2py orbital on carbon 2. It can't be on carbon 2. In this combination, there can be no orbital, no electron density on carbon 2. Yeah?
Why wouldn't it be like that for the first one?
Because for the first one, this is not a node. Yeah, see, for the first one, the phase is the same between 1 and 3. So you can mix in something on 2 either way. But because of this minus combination, the node lies along carbon 2. There's nothing we can do. And actually, we'll just put the big X through that, because we can't do it because carbon 2 coincides with a node. And so that our third orbital looks just like this, and is still just the minus combination, because whether we add or subtract 2py there for carbon 2 doesn't make any difference. So now we've got three orbitals, and these are their relative energy levels. Sometimes, because we're tired of writing all of this stuff, we'll call this pi1, pi2, and pi3. And if we were to make, Joshua, sorry, I got confused. I thought I was somewhere else, which I'm clearly, okay, this was pi1. I wanted to move this to be sort of in between the two. This is pi 2, and we'll call this pi 3. If we had an energy diagram, we could sort of rank them like this: pi 1, pi 2, and pi 3. Now, depending on how many electrons you have available in the pi system, you can fill up the available orbitals. In this cation, we have 2. So the LUMO is pi 2. And it's only on carbons 1 and 3. Incidentally, those of you who are teaching undergrads about resonance will note that this is a classic example of a case of resonance where the positive charge can be on carbons 1 and 3. Valence bond theory tells you exactly what MO theory tells you, which is that the reactive part of that molecule is on carbons 1 and 3, but not on carbon 2. The LUMO is only on carbons 1 and 3. Similarly, if we were to do allyl radical, pi 2 would be the singly occupied orbital. If we were to do anion, pi 2 would be the HOMO. Yeah?
So if we have a cation, we can kind of think of it as having like a p orbital.
If you see a cation on an sp2 hybridized carbon, you can think of there being an empty p orbital on that carbon. Yeah. Okay, what else? Yeah.
So the empty p orbital. So is that why it's synonymous to it having a node there, or is that totally different?
So I guess the empty p orbital, is it synonymous to having a node on carbon 2? No. What I mean by empty p orbital is just what we did for the group orbitals for planar methyl. You'll recall we had a sigma, we had a pi orbital, and I think we had left over, well, sorry, I'm gonna have to go back a couple of days. When we even further, that's fun. When we first did group orbitals for methyl, sorry, I'm getting lost. For planar methyl, we had 2 pi type orbitals, and then left over we had this 2pz orbital. And in the case of methyl cation, which only has 6 valence electrons, that 2pz orbital would be empty. Now, when you look at that allyl carbocation, when you see a positive charge on just a localized carbocation and it's sp3 hybridized, then yes, you can think of that carbon as having an empty p orbital. It's not correct to think of that in the case where the positive charge is resonance stabilized. Because you're right, technically you could think of a p orbital being on this carbon, but it's adjacent to a pi bond. So that means you actually have 3 p orbitals in a row that we're going to mix together. Which is why we just took care of that from the beginning. Other questions?
I think that I just missed this, but the electrons that you were putting into the orbitals over there, which electrons are those representing? Because that's not all of the electrons.
Right, only the pi electrons. Because we're ignoring, because the sigma bonds or because the pi orbitals are orthogonal or 90 degrees away from the sigma type orbitals, we can ignore them if we're only interested in the pi orbitals. How do we know that the pi orbitals are higher in energy than the sigma orbitals? Well, because pi bonds are less stable than sigma bonds. Yeah. Okay, what else?
And you
Yeah.
said, so the second carbon is unreactive because of the node that's there.
Right.
And
Or another way of saying that is the LUMO is just not on that carbon.
Okay.
Yep. So if this were going to be an electrophile, the nucleophile could attack at carbon 1 or carbon 3, but not carbon 2. All right. You can do this, and maybe it would be a sort of a, I'm going to draw quickly for you the pi orbitals of 1,3-butadiene. I won't show you how we get them, but they look like this. I'm going to have to draw a lot of p orbitals. Haha, I'm going to... No, today I won't copy and paste. I'm going to be nice to you. We will all draw all the p orbitals together. And again, the way I'm drawing these pi orbitals is only meant to communicate which p orbitals we add together to make the pi system and in what combination, plus or minus. So the lowest energy one, as you might imagine, is all in phase. The next, or all with the same wave function sign. The next one only has one node and looks like this. The next one has two nodes and looks like this. And then the last one has three nodes. And because we like to color, we're going to waste precious lecture time filling in yellow instead of just moving on. I've tried and tried to resist the temptation, but what are you going to do? All right, so these are our pi orbitals. We could call them pi 1, pi 2, pi 3, and pi 4. Go ahead and count the nodes and convince yourself you've got 0, 1, 2, and 3 nodes. We could say what their energies are, but we'll just sort of space them out like that. In 1,3-butadiene, we have 4 electrons in the conjugated or adjacent to each other pi bonds. So HOMO is here, LUMO is there, and at some point, if you haven't already reasoned through it, understanding this will help you understand how the Diels-Alder reaction works. But what I want you to do later on is figure out if you can use the orbitals, the pi orbitals. I think in our diagram of ethylene, I think we called it a 2py plus 2py and the 2py minus 2py combination, but use those orbitals from ethylene to make these ones and see if you can get those answers. The first one is easy, right? Side by side 2py plus 2py with another side by side 2py plus 2py. So see if you can do that. That's kind of fun. Okay. Other questions? All right. Let's talk about cyclopropane. This one's kind of fun. I keep saying that. Kind of, which here means not much, but there are some insights to be obtained. So cyclopropane, by definition, is this lovely equilateral triangle. And one of the troubling things about cyclopropane is that if you want to stick with valence bond theory, you got a problem with bond angles. By virtue of the fact that this is an equilateral triangle, the internal angles, bond cyclo, how do you spell propane? Okay, propane. Spelling on the fly is not my strong suit. So these internal bond angles all have to be 60 degrees. Nevertheless, you would be, because each of these carbons is surrounded by 4 groups, you would want to call them sp3 hybridized, but the most favorable bond angle for sp3 hybridization is 109.5 or something like that. So these are clearly not tetrahedral carbons. And so sometimes we come up with this convoluted picture whereby we're just sort of cranking on one of those carbons, making it sort of bring its orbitals in like that. And thinking of these as being sort of mostly sigma bonds. Nevertheless, cyclopropanes have interesting reactivity, and in some contexts, it looks like there's maybe some pi bond character to cyclopropane, and we'll talk about that later. But consider another way of thinking about cyclopropane. Consider taking 3 bent CH2s. So here's, and we're sort of looking at it on its edge. So there's one bent CH2. Here's another bent CH2. And here's another bent CH2. Lining them up like that. And that would sort of account for the 120-degree bond angle between those hydrogens, which you can measure if you look at cyclopropane. And we could ask, what does that do to bonding in cyclopropane? You get the, I want to pause just to make sure you're with me on the concept so far. So we're not dealing with hybridization. We're just going to deal with the group orbitals, because hybridization is a valence bond theory concept. We're going to do this in an MO sense, and we're only going to use the group orbitals for bent CH2. And these are the ones that we have. But this is the alphabet of orbitals that we're going to be able to use. Only we've changed our perspective a little bit. When we drew the group orbitals this way, x-axis was up, z was to the left, and y was coming out at us. Now we've sort of, now we're sort of looking down. Why can't we write? Now we're kind of looking down the x-axis. So it's like we've tipped each of these up on their edge. So let's think about the combinations we could get if we combined 3 of these sigma CH2s together. And for the sake of our discussion, I'm going to draw, where possible, the sigma CH2 orbital kind of like this. Even though it comes from a 2s on carbon and 2 1s orbitals on hydrogen, you get a continuous lobe of electron density that envelops that. Okay, so kind of like we did with allyl carbocation, we're going to mix 3 orbitals together. We could get these 3 sigma orbitals. We could have the all plus combination. I'm not going to write the CH2 3 times. What would that look like? Well, you'd have 3 of these lobes approaching each other. And maybe with a dotted line, I'll just indicate what we're typically calling the bonds, even though those are now just lines that connect the carbons so you can tell they're next to each other. What would this look like if we drew this molecule in Spartan and then sort of asked what this lowest energy orbital would be like? Well, I don't know why I'm erasing stuff. Probably now we have one continuous lobe of electron density that envelops the whole molecule, all with the same wave function sign, and I'm going to need a bigger paintbrush to do that. Okay, so let's go ahead over to Spartan and see what we can see if we make cyclopropane. There's a chance that it won't have cyclopropane in the database, and then we'll just have to be sad. Ah, good. All right, so see how we can sort of think of this as 3 bent CH2s just sort of pointing together. Look at the MOs. The lowest energy one is just like overlapping all of those sigma CH2s in phase. Now, you have to deal with the minus combinations, and I don't necessarily think it's worth our time to do all of those. So what I will do is just walk you through some of them. This orbital we get by having the bent CH2, the sigma CH2 here and the sigma CH2 here be with the same wave function sign. And then the third one is opposite. That's one of the minus combinations. And then the other minus combination looks like this. If you have this one be opposite to this one, then there's a node right in the middle and there's no density on that one. Both of those orbitals have one node, and so they're degenerate. Next, you have next we're going to combine the pi CH2s together. So I will do one of those, and then we can discuss the other couple. What does the pi CH2 look like? Well, when we're looking at it on its side, you have a lobe on top that envelops the space between the carbon and the hydrogen, and a lobe on the bottom with opposite wave function sign. What that would look like here would be a lobe like this and a lobe like that below the plane of the page. And then we would do the same here and the same here. And if we looked at this and asked sort of how does that actually look, we would see something like this with opposite wave function lobes above and below. Oh, the page, thought I hit that one. So we're with whatever this sign of the wave function is up here, and then below that, need bigger font. Okay, and that is, so that's bringing the 3 pi CH2s together side by side, all in phase. And that's what we have here. There's the plane of the ring. Here is one of the pi CH2s, carbon and hydrogen there, carbon and hydrogen there. You get that from combining a p orbital on carbon with the 1s orbitals on hydrogen. See where that comes from? And do you see how that almost looks like a pi bond in between each of these carbons? I told you this molecule has some pi character. That's a fairly low energy orbital, but that's not a sigma bonding orbital, right? Now, the other there are two combinations up here you might guess that we're going to get from the same types of things we did here, right? You're going to add together, in this case, 2 of the pi CH2 side by side in phase, and then the other one has opposite wave function signs, so there's a node in the middle. And the other one looks like this. You're going to have the 2 pi CH2 side by side, but with the wave function change in sign, oh dear, and a node that corresponds to the other carbon, so there's no electron density there. All right. Um, excuse me. So let's talk about let's talk about what we do with the sigma outs. So here is a sigma out orbital. If we're looking down at it from above and sort of combining them together, what would we expect to get? And this would be the all plus combination. Well, the sigma out looks something like this. There's a lobe on this side of the carbon, and then there's another lobe in the middle. A lobe on this side that envelops the hydrogens, and then a lobe in the middle. A lobe on this side that envelops the hydrogens, and then a lobe in the middle. The cool thing here, the cool thing here is that the sigma outs are pointed in exactly the right direction if you wanted them to overlap without any worry about sort of having to bend orbitals. They're pointed right to the middle of that ring where they can overlap with each other. And indeed, so this would be the combination of sigma out plus sigma out plus sigma out. I guess I'll annotate this. This is pi CH2 plus pi CH2 plus pi CH2. All right? And indeed, if we go to Spartan, that's what we see. Here's the lobe that envelops the two hydrogens on the backside of carbon, and here's the part that points to the middle of the ring, and that's happening on all of these. So for those of you playing along at home that enjoy Star Wars and the animated series Rebels, where Grand Admiral Thrawn develops a new variant of the TIE fighter called the TIE Defender, and it has 3 wings. It kind of looks like that. So we're nerding out here, sorry. Okay, there are a couple of out of phase combinations of the sigma out orbitals, but they're high enough in energy that we can not worry about them. And they are not filled. Okay, so we've dealt with the plus and minus combinations of sigma CH2, pi CH2, and sigma out, though we didn't draw, or I didn't show you the minus combinations because they're high enough in energy so as to be unfilled. That takes care of 3 parts of our alphabet, but we still have the 2py orbital. This is weird because notice if these are both hydrogens, those 2py orbitals are pointing out sort of orthogonal to that CH2 group. So from our perspective, looking down from above, maybe I'll just copy this one. From our perspective, looking down from above, and I'm going to start with just one of the 2py orbitals on this carbon, that's going to be in the plane of the page, pointing out in that direction. So that's not even pointed at the space between the carbon atoms. That's sort of splayed outward. Okay. So what might we do? Well, you could imagine having 2 of them sort of side by side and sort of angled towards each other, and you could imagine that there might be some overlap there. Okay, so we've got a 2py plus 2py. What are we going to do with the other one? We're in a tough situation here, right? Because no matter what we do, there's going to be a mistake in the phase, right? There's going to be an out of phase lineup. So we can pick one. Oops. Okay. So if we sort of look at this carefully, what do we see? Well, if we were to draw what this looks like, it would be like we had a lobe of electron density in the plane of the page, but hovering on the outside of that ring, and another one here. And they would have opposite wave function sign. And then here we're going to have two other lobes that are also opposite in sign with respect to each other, so that we have a node going through that way. And we also have a node here along those two carbons. Okay. So that would tell you that in cyclopropane, though we've drawn it as this triangle, there's some serious electron density out here. Sometimes people call those Walsh orbitals or so-called bent bonds because the orbitals are not overlapping end on end. The other, let's see. Trying to figure out what the other combination is. So if we go here, one of the highest occupied molecular orbitals looks like what we just drew. I'll zoom back over to notability. That's this one that we drew. Two larger lobes along two sides of the triangle, and then on the third side you have two smaller lobes that are out of phase. And that's what we've got here, the two larger lobes and then the two smaller lobes. The next one that we get is a little bit tricky, and I'm honestly not sure where it comes from. So I'll do my best, and then we can just sort of move on from there. But because it has the same number of nodes, it ends up being about the same. So let's see. I actually think, since I don't understand it, that I won't even worry about it. Okay? So sorry about that. You get this other combination from considering, basically we're in a situation where it doesn't matter whether we add or subtract the next one. And you get the third orbital. What it looks like to me is almost like you've combined two py orbitals on these two carbons with maybe a sigma out orbital there, and I don't know why. So I am sorry and confused. In any case, this particular orbital, which is one of the highest occupied molecular orbitals in cyclopropane, explains the unusual stability of cyclopropyl carbocation. So if you'll allow me, I'm going to take this and we'll put it here and we'll spin it around. I realize that does bad things for our carbons. I'm going to draw here the Lewis structure of the cyclopropyl carbocation. And to facilitate this discussion, we're going to talk a little bit about carbocation stability. Cyclopropyl carbinyl carbocation involves a methyl group or a CH2 group that you've added adjacent to the cyclopropane ring. Notice this is a primary carbon. Normally you wouldn't draw primary carbocations. You'd think they're too unstable to be reasonable intermediates. We're going to learn in chapter 2 that one way of assessing carbocation stability is through something called hydride ion affinity, which is a gas phase measurement. It's measured in kcals per mole, and it tells you how much a carbocation wants a hydride. The more unstable the carbocation is, the more unstable the carbocation is, the more it wants the hydride, the higher the hydride affinity. So just to sort of keep things in perspective, if you take a molecule that looks like it's related and put the positive charge here. Same thing as this, only we don't have a bond there. That hydride ion affinity is 265 kcals per mole. In contrast, the cyclopropyl carbinyl carbocation has a hydride affinity of 249 kcals per mole. So that's a fairly substantial difference. And again, just to put that in context, if you had a primary carbocation that, the hydride affinity is 273. If you bring resonance into the picture, it goes down to 256, right? So I'm not really great at arithmetic, but the resonance effect here, 14, 17 kcals per mole, and it's like 16 here, right? Sort of, ish. Yeah. So it's almost as though, in terms of hydride affinities, this cyclopropyl carbinyl carbocation looks like it's resonance stabilized. Now, what the heck is going on there? If you don't have the MO picture, you can understand it, but it becomes difficult. If you do have the MO picture, suddenly it becomes quite simple. So what I'm going to do to generate this is I'm simply going to replace one of these hydrogens with a CH2 group, and it's going to be a bent CH2 group. This is sort of hard to represent, but a hydrogen will be coming out at me here and going back into the plane of the page. And one of the orbitals on that bent CH2 group is the 2py orbital. And we can place it so that it lines up side by side with with one of our 2py plus 2py plus 2py orbitals from cyclopropane. What that means is, and I should point out that in cyclopropane, this orbital is filled. All right, so we're just going to call this, we need a name for it that isn't challenging to write. We'll call this maybe pi1, as we've drawn it. Pi1, if you looked at Spartan, it's one of the two HOMO orbitals, so that means it's filled. Got 2 electrons in there. So what we've drawn here is the combination of pi1 from cyclopropane with the 2py from that CH2 group, and that combination will be filled. And that's stabilizing, right? When you mix 2 orbitals together, you get a filled combination and an empty combination. The minus combination of these two, which would be an empty orbital, would simply have the p orbital on the carbon out of phase. And this turns out, and it would be, now you'd be, the combination of 2py minus the pi1, that's going to be an empty orbital. We're going through pretty quickly, and I apologize for that. But the point is that these bent bond type pi orbitals that we get out of cyclopropane explain why it's okay to have a carbocation at that adjacent position. And if you actually do the math and do the calculations for this carbocation, this is the HOMO and this is the LUMO. Okay? Now, questions you want to ask about that? You didn't know cyclopropane was sort of like having an adjacent pi bond, This kind of phenomenon turns out to be important in cholesterol biosynthesis, and maybe I'll show you that. I'm not prepared to do it now. It's not off the top of my head. But that kind of involvement in bonding of this extended group of carbons can be important. Now, I suppose we could ask, how does valence bond theory deal with the cyclopropyl methyl, carbocation? And the answer is it does a little bit, but it gets a little challenging. So it'll be most useful, I think, for us to consider this by looking at this molecule on its edge. So looking at the cyclopropane from the side. Oh, that looks terrible. Shall we try again? Dang it. The dashes and wedges don't really do us any good here. All right, this one's going up, this one's going down. Back here you have one going up versus down. Here you have one, and then I'm going to draw the CH2 group that's positively charged here. And simply put the positive charge there. So the way that valence bond theory deals with this is it envisions resonance structures. So I'm going to copy the same orientation of the atoms, only I'm going to take this sigma bond and I'm going to have it bond with that carbon. Everything's in the same place. I'm just saying that. And that would somehow communicate what the MO picture tells us, which is this carbon is involved in bonding with that one. Yeah.
Does that mean the plus is on the like?
Sorry, yeah, if you're going to draw resonance structures, you got to put the plus. Yeah, you would put the plus there. Sorry. Similarly, I could take, I don't know what color to use. I could take this bond and instead of putting it there, I didn't like that either. I could put it here, and then the positive charge would again be here. Yeah.
This reminds me of when we were doing organic chemistry, like there would be some reactions when we were dealing with like cyclic structures, and if it was like cyclopropane or cyclobutane, and when we were doing reactions and we had like a carbocation, then we could increase the number of carbons in
Ring
the cyclic
expansion.
structure, so that we said that because that is going to be more stable and for it that way.
Yeah, so you could imagine then if you had this positive charge next to this ring, you could imagine reactions in which you just move this bond over. Now you got a 4-membered ring, and then maybe a nucleophile comes in there. And these kinds of reactions are known. What people will sometimes do, and I'll show you another, dang, it's taking too much. I just keep talking and talking and talking, and then we can't. We can do a third resonance structure where we make a pi bond here and put a positive charge here. So what sometimes people will do for cyclopropane, I'll draw it now from this perspective, and this gets horrible. They will draw the hybrid structure this way. Dot, 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 dot. Guess what else we're going to do? Dot, 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 dot. guess what else we're going to do? ... with potential positive charge here, 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 and there. This kind of carbocation is called a non-classical carbocation in valence bond theory, because you have a single carbon that looks like it's bonded to 1, 2, 3, 4, 5 things. Texas carbon, y'all. Okay, so we'll leave you with that painful and strangeness. I guess we're still not done with chapter 1. I really meant to finish with it soon, because that means there's other stuff we won't get to, but I'm having too much fun. So we'll stop there and we'll pick it up on Friday.